Okay, I'm going to show you how to run a heat test case from the terminal using the appImage in this video. So let's start with looking in our test case folder. So this is the tarball, the testcase.tar.gz that we downloaded from the GitHub page, and we extract that and it creates this v2.0 folder or whatever version you are on. And then in this folder we have the batch file, and that's going to describe our terminal run. I'll talk about that in a second. And then we also have this folder which has NSTX. It has a machine name, and in it are a bunch of files that go to that machine. You could also have another folder like, say, D3D if you wanted to do multiple machines, and you could put the files for D3D in that file. So for today we're just talking about NSTX, so it's fine to just have this one folder. So I'm going to start by describing this batch file. I have that pulled up back here. What you can see is it's basically just a big comment in the beginning, and then you have, starting down here, you have two lines that are not commented, and the first line is column headers. So you have match flag, tag, GEQDisc, CAD, PFC, input and output. And then the second line has all of these different values that correspond to the columns. And this whole commented section here goes through each one of the column headers and sort of describes what that column is. So we can see that this is the only line that is uncommented that isn't a column header line. We do have this other one that's commented here that we could uncomment if we want. But every line corresponds to a different heat run that is going to be performed when we run this case, when we run this batch file. So there could be a batch of heat runs that we run from a single file. So for this case we have just one, and it's machine NSTX. We give it an arbitrary tag, so I've called this one run1. We could also call it like optical run1 or something like that. We have a GEQDisc file, and if we look in this directory, we can see that that GEQDisc file is in that directory. So in the NSTX directory is this G file. Also in that directory is this test case step file. We have a PFC file. We have an input file. And then this final column is the things that we want to calculate. And those are defined up here, your options. So we're going to calculate the optical heat flux and the temperature, as you can see right here. So like I said, every one of these lines corresponds to a different heat run. So if we uncommented this line, then we would do a second heat run after we completed this first one and call it run 2. And that would be with this G file, the same CAD, but a different PFC file. So this says gyro, so that would lead you to believe that it was for gyro orbits. And then this is a gyro orbits input file, and you can see we have an optical heat flux and a gyro orbit heat flux. I'm not going to do that today. There'll be a different video about gyro orbits, so we can leave that uncommented. The only other thing I'll note about this file is that if we had multiple time steps for the same shot, we could put this G file in and then just have the run, the tag, be the same. So if you have the same machine flag and you have the same tag, heat knows that that means that this is a time varying run with multiple EQDisc time steps, and so it will group them together in a single run if they have the same tag. And the step file will always be taken from the first line. The PFC file will always be taken from the first line, but the input file, where you have things like psol and scrape off layer power or lambda q, things like that, can vary. So at each time step we'll read this file and update all of the parameters inside of it. And then we have the you should keep the output the same. So this is going to be the first line is what's going to be the output for all of the lines. So I'm going to just delete this out of here right now, and we will go ahead and set this up and run it. So if we look in this folder again, remember this is the folder that has the that we extracted. So it's the tarball, we extracted it, it has this v2.0 folder, and inside of it we have this NSTX folder. So we have 2 GEQ disks, 2 input files, 2 PFC files, and a step file. And so like I said, those are all defined and called out in the batch file. I'm just going to go through these really quick. So the input optical CSV file, each one of these lines corresponds to something like a input from the GUI, if you're familiar with the heat GUI. And so I won't go into what each one is. If you want to see the video on the GUI, that will sort of tell you what everything is in terms of the inputs. But each input corresponds to a different thing here. So like, for example, which heat flux mode are we going to use? This is saying we're going to use Ike's regression number 15. Yeah. And then for the PFC file, it's a standard PFC file, just like the old version of heat or the GUI version of heat, where we have, again, a huge comment here, and then we have a bunch of columns, and these are the headers of the columns. So we have time steps, 0 through 5,000, so that's saying we're going to calculate the heat loads between 0 and 5 seconds. This is in milliseconds is the unit. We have this PFC, and so if we look at the CAD here, that's this PFC in the middle. You can see its name, solid 843 here. So that's where we want to calculate the heat flux. We're going to do a resolution of 5.0 millimeters. We're tagging it as the lower outer diverter, and we're going to check for intersections against all of the PFCs in the CAD. And so what you'll see here, I have one hidden, let me turn that on, is that we have several PFCs in this step file that are sort of unphysical, these planes, and those are just there to constrain the problem. So instead of including all the backing plates, for example, underneath this tile, I've just included a plane to simplify the calculation. And then I have this plane on top, which is a gyro orbit plane. And we don't need this for this optical calculation, so it'd be great if we could just sort of turn it off. And that is what we're doing in this final column, this exclude name column, where we exclude the gyrosaurus plane. So once we have this PFC file set up, we have our input file set up. Oops, it's this input file. And our batch file is ready to go. We can actually go about running this. So I'm going to change directories to where my appImage lives. So in this case, it's in this directory. And I'm going to start it by typing in the name of the appImage. This one is 2.0.0. And then I have some switches. So if I just run it like this, it will run GUI mode. If I want to run in terminal mode, I need to do -M switch for mode. And this can be a G or it can be a T. So we're going to go with T. G is for graphical user interface. T is for terminal user interface. And then I'm going to give it the path to the batch file. So a -F flag, and then the batch file lives at /home/tom/btest. So you'll need to edit this to match your specific location where you downloaded your batch file. And I think that's where I downloaded mine. And it's called batch file.dat. Okay, and so this command should pull this batch file and run all of the lines that we described a few minutes ago. So if I run that, you can see it launches heat. It says we're in the terminal user interface, and it starts marching through, and it's going to start solving the, so we can see we're running tag 1 first. So I'm going to scroll up a little. So it's running machine NSTX tag 1, and here we are, we're marching through doing our field line traces. So it's just going to chug along. I think this one is for 10 degrees. So I'm going to pause the video, and then I'll start it back up when we finish. Okay, so the heat run just completed, as we can see here. It ran through this thermal analysis in the end, so it gave us the temperature simulation. We see at the end here is the max temperature. So we can go ahead and open pair view and look at some of these results. So I already have this CAD open, even though it's a little bit lower resolution, that's okay. And you can see that there's going to be something different about this one from if you're running heat in the GUI. Also, sorry if you hear my dog snoring in the background. So NSTX _204118, that was the shot we ran, but our tag has been appended to the end. So remember the tag from our batch file here? That is the same tag that gets appended at the end here. So I'm going to open that folder. I'm going to look in the the 4 millisecond is what we were running. These are from some previous runs I did. So in that folder, we're going to look at the ParaView optical heat flux, and it should be a 5 millimeter optical heat flux calculation. And there we have it. And remember, we don't have all the CAD in here, so that's why you're seeing some heat fluxes down here. But we did have the plate on the bottom, that plane, remember, here's the CAD. So there wasn't really much to constrain down here, but there's this plane I put down there. And for 10 degrees, we're probably only making it down, a few millimeters. So these results make sense, and we can look at the temperature simulation too. So if we just go up to run 1, and we go to open foam, heat foams, solid 843, that's the name of the part, and open the foam file, we have all these different arrays we can load. We'll just load all of them. And I'm going to turn off the STL, and we can see this is a pretty chonky mesh. If we look back in here, in the input file and NSTXU input optical, down in the open foam variables, we had a min and max mesh level of 1 and 2, which means it's a very coarse mesh. If you increase those numbers, it will, to say 2 to 5, that would be a much finer mesh. But this one was just to prove that everything's working, so it'll do the trick. We're going to change to temperature, and we can see that the peak was at 4 milliseconds, so we'll go all the way back, and then we'll just march our way forward to 2, to 3, and then to 4, and that's when it peaks out here, and then it decays off afterwards. So that makes sense. So yeah, that is how you run heat from the terminal. And if you wanted to do multiple runs, you could just uncomment these lines. You could also put in different machines. Like for example, we could do a run 2 that's for D3D and edit the G file, obviously the step file, the PFC file, and the input file. And so you can do multiple machines in a single heat command. You can do multiple of the same machine. You can do multiple time steps. Remember, if you want to do multiple time steps, you do the same tag. So really, the sky is the limit in terms of the heat simulations you want to run. And yeah, if you have any questions, feel free to email me. My email is on the GitHub page. So feel free to drop me a message if you run into problems. So thanks for watching. Hope this was helpful.